In this section, we're going to talk about functions and review what we have previously learned about functions. It seems like every different textbook has a somewhat different view of the definition of function. Here's the most simple definition of function I've ever seen. It's based upon a definition for relation. Let's define a relation as a set of ordered pairs. A set of ordered pairs. Now the set can be as simple as this little set of ordered pairs, a set consisting of these three ordered pairs. That is a relation. Now a relation could be a set that is defined by some kind of equation involving a couple of variables. And in that circumstance, the set of ordered pairs would be an infinite set, presumably, if we're talking about real number replacements for those variables. At any rate, with this set of ordered pairs, and we're going to use as an example our simple set of ordered pairs here, the domain of that relation is the set of first elements. So the set consisting of the first elements in this set of ordered pairs. So it would be a set consisting of 2, 3, and 4. So the domain of that relation would be the set of 2, 3, 4. Now, a lot of times in this situation, in this environment involving relation and function, we talk about variables x and y. Now, a lot of equations involve other letters, so we don't want to just etch in stone the idea that it's always going to be x and y. But if we're thinking about domain, it would be the various values that x can take on. And in this situation, if we're talking about a variable that's x or another letter, then this variable is said to be the independent variable. So the independent variable is associated with the domain. That's the idea. Back over here, the range is the name given for the set of second elements in the relation. So the range, the set of second elements. For our little relation here, it would be a set consisting of 4, 6, and 8. 4, 6, and 8. And the variable involved here is sometimes called the dependent variable. Now, there isn't any big mystery about independent and dependent variable. It's just a couple of terms that are used to associate these ideas. You know, if we have an equation that is in the form of y equals and then 2x minus 3, something like that, then we have, as you know from before, y is a function of x, and we'll talk about function in a second. But you know, in that circumstance, if we're graphing, a lot of times if we're using the point plotting method, we choose values of x and then we determine values of y. So we sort of choose values of x at random, you see, independent. So we just choose them out of the sky, and then the values of y that come from those values chosen for x depend upon the values that we chose for the x. So the y value, the second elements depend upon the first elements that were chosen. And in that way, it's pretty easy to remember independent and dependent variable. We're ready to talk about function. A function is a relation. So a function is just a special kind of relation. It's a special kind of set of ordered pairs. It is a relation in which for every element in the domain, for every first element you see, there is exactly one. That means one and only one. There exists one, but there exists only one, you see, element in the range. And that's really all there is to it. If we're talking about x-y pairs, then it just means for any x that's in that domain, there is one and only one partner named y, or from that set of variables y that is its partner. There is no other partner for that x that we chose. All right. There are a number of ways of showing a relationship or presenting a relation involving a couple of variables, and let's say x and y for the moment. This is one way. Here's an equation that gives a relationship between x and y. If we want to evaluate this equation for y, though, it's kind of convenient to solve the equation for y, to isolate the y on one side of the equal sign. And we can do that by subtracting x squared on both sides and then going through and dividing by 2. And in which case we would have this, y equals 1/2 minus x squared over 2. Now, this is called the explicit form. We are explicitly showing actually we're showing y as a function of x here. This is called an implicit form. When we solve it for y or have y isolated, it's an explicit form. The notation that involves the function idea is this f of x. We say this is f of x. It doesn't mean f times x. Remember, f is the name of the function. It could be f or g or h or another letter name that we give to this. And this simply tells us what the independent variable is. So this is the name of the function, and this is the independent variable. And here is the behavior, I guess we could say, for that. And the dependent variable, the set of dependent variables, the range of values would be given by this f of x, you see, which replaced y. And these are interchangeable parts. We can go from one to the other. The function notation is pretty useful, though, if we're going to evaluate this function for a certain replacement for x, for a certain value of x. If we're going to evaluate for the value x being 3, then we would write this as f of 3. And this is a very specific request. It says that in the f function, in the function that we named f, replace x with 3 and evaluate. Or what is y when x is 3? That's all it's saying. And to make the evaluation, we replace x with 3 in the expression over here. And then we would simplify and find f of 3 to be negative 4. Now, the x here, the independent variable that we're calling it, there isn't anything mysterious about that. We could replace x with any letter that we would like. We could replace it with a symbol if we want to. It's just a place for replacement, really, is all that it is. Here, for example, let's call this symbol twiggle. This is f of twiggle. You see, and f of twiggle is this expression. Notice twiggle is squared here. So it's just a place for a replacement. So in this f function that we're talking about here, f of 3 means replace twiggle with 3. So it's the same thing that we had before. Take a look at this g function. It says g of x is x squared minus 3. G of 0 means in the g function replace x with 0 and evaluate, so this would be 0 squared minus 3. And then g of 0 would be negative 3. Here, this says g of a minus 2. Now remember, in this notation, what appears in parentheses here means that we're going to make a replacement, and it's a blind replacement. Whatever appears in the parenthesis needs to replace the independent variable. So this is saying in the g function, replace the x with a minus 2. So in place of this x, we're writing a minus 2, and we'll have a minus 2 squared then minus 3. Just remember, it's a blind replacement, and from here we would just perform the indicated operations. A minus 2 squared, a squared minus 4a plus 4 minus 3, collecting a squared minus 4a plus 1. So g of a minus 2 would be this expression. Let's talk about domain and range. Sometimes we need to identify those two sets. And let's talk domain first. Sometimes when a function is just given like this with no description of a domain, then the domain is implied by the nature of the equation. And you can think algebraically that domain means the acceptable replacements for x. What x values are acceptable to replace in this function or in this expression? Which ones make sense? Well, every real number replacement makes sense here. We could replace x with any real number available to us, and this expression makes sense. So the domain would be all real numbers. And it is implied, it is implicit here. Now, in other circumstances, the domain is given or written for us, and in those circumstances, we say that we have an explicit domain. It is not implied, it is stated for us. So in this function, the domain is given as x values between negative 2 and 5, including negative 2, not including the 5. So implicit and explicit ways of describing domain. Let's talk further about domain and range. Most of the time, identifying domain is just a matter of looking at the expression involved and saying what are the acceptable replacements for x. And a lot of times the range is a little more difficult, a little more elusive for us to identify, because for the range we're having to say, well, for these acceptable replacements for x, what values of y, you see, are coming out of this? What values occur when we replace x with those acceptable replacements? Well, let's go through the whole process here with this function. We have the square root of x plus 3, domain, acceptable replacements for x. What values of x are acceptable in this circumstance of square rooting? Well, for what values does the square root make sense? The square root of what numbers makes sense? Well, we can take the square root of positive values and 0. We can't take the square root of negative values, you see, in the real number system. So we say that we would like to select x's, or the x's that make sense as replacements here would be those that will cause the radicand to be positive or 0. And this radicand is positive or 0 when x is either negative 3 or greater. So the domain then, and there are a lot of ways of writing this, but I'm just going to write it in the simplest way possible, the simplest way I know of possible. X is greater than or equal to negative 3. You see, now we could use set notation here and all this kind of thing and say that x is an element of the real number system, you see, and x appears in this interval of our real number system, but it really isn't a necessity. So x is greater than or equal to negative 3. Now, what about range? Well, when we take the square roots of these positive numbers or 0, what kinds of values come out of that? You see, what are the y values that occur under that circumstance? Well, the y values that occur are y values that are either positive or 0. When we take the square roots of numbers, we always get a positive number, or we could get 0. So the y values then will be greater than or equal to 0. That is a way, not the way, of stating this. Once again, we could use a set notation here to describe range, and some teachers will want to do that. Well, we're looking at domain and range now algebraically, and we also want to look at it graphically. And let's slide over and look at the graph of this function and decide on domain and range. It turns out that it's easier to look at it graphically, maybe sometimes, than it is algebraically. Graphically, we are saying for domain, for what values of x do we have values of the graph, or do we have the graph defined? And this graph appears horizontally in the region of the graph of the coordinate plane from here out to the right. So it's from negative 3 out to infinity, you see. So the domain is x greater than or equal to negative 3. It just verifies what we had over here. In a similar way, for the range, we're talking about for what vertical distances do we have a graph? You see, is the graph defined? What vertical distances on our coordinate plane do we have a graph? Well, do we have an x corresponding to that vertical distance? Yes, it's out here. Do we have an x corresponding to that vertical distance? Yes, it's right here. You see, and for all of these values of y, we have x values that put spots on the graph. For these down in here, we have spots over here. Do we have places on the graph for y values down here? No! And therefore, the range would be values of y that are only from 0 up, or y is greater than or equal to 0. Just verifies what we found over here algebraically. Let's look at another one. And incidentally, these are the two classics. A radical type of function, or a function that has a radical in it, and here we have one that is rational. And for the rational function, let's see, the acceptable replacements for x is what we're talking about for domain. What values of x make sense for a fraction? Well, fractions make sense for just about any value except for a value that would cause the denominator to become 0. We disallow values of x that would cause denominators to become 0, so this denominator cannot take on the value 0, and the x therefore cannot take on the value of 2. So it would be all real numbers except 2, and we can say all real numbers except 2, or we could say that x is not equal to 2. Now what about the range? Well, now here, this is really elusive. For what kinds of results do we get when we replace x here with anything except 2? What values can this expression take on, You see, well, it turns out that it can take on very, very large positive values, very, very small positive values, very, very large negative values, very, very small negative values. The only value it can't take on, it turns out, is 0. That this expression can never become 0. Expressions or fractions become 0 when numerators are 0, and there's no variable in the numerator to affect the value of the fraction and to cause it to become 0, so it can never become 0. So the range would be x is not equal to 0. All real numbers except 0. Let's look at the graph. The graph is especially interesting in this kind of problem. It has a lot of character. Rational functions, remember from your work in algebra, are often characterized by having asymptotes involved. And there's a vertical asymptote at the place that causes the denominator to become 0. So we have a vertical asymptote at x equals 2. And the asymptote is just a line that the graph tends to snuggle up with at the extremes of the coordinate plane. So the extremely up and extremely down, the graph gets really close to that asymptote, but never touches it. And extremely down, you see in the south side of the graph, the coordinate plane, the graph gets really close to the asymptote as well. So in terms of domain, in thinking about what values of x put points on the graph. You see, here's the value of x and here's a point on the graph. Values of x out here, point on the graph. Values of x out here, point on the graph. Over here, value of x, point on the graph. Value of x, point on the graph. All of these x values give points on the graph. All of these x values give points on the graph. But 2, x being 2, does not give us a point on the graph. So it's all real numbers except for 2. Now, in a similar way, identifying range, range is, we're just kind of twisting our thinking and saying, for what y values do we have points on the graph? Well, for this y value, there's a point on the graph, and for that one, and for this one. And down here, we have points on the graph for all of these y values. But we don't have a point on the graph for a y value of 0. And it just verifies what we found earlier algebraically. Here's a function that is defined in parts. This is sometimes called a piecewise function, or it is defined in terms of intervals. And I think that's maybe the best way to describe it. It says f of x has this kind of description when x is less than or equal to -2, but we're describing our function this way when x is greater than -2. So it's defined along intervals of our coordinate plane. Now, all we're doing is constructing this graph on that interval and this graph on this interval when we look at the graph. And we're going to talk domain and range in a minute, but let's talk about the graph. 2x plus 5 in this interval means that straight line for the graph, or that line up to this point for the graph. Here's the point -2, you see, and it's defined up to that spot. And then for x squared minus 3 for the interval from -2 to infinity, not including the -2. So it's from here and then all the way out this way. So the graph looks a little peculiar, but now by looking at the graph, can you tell what the domain is? Sure, you can. For every value of x, we have a point on the graph, you see. And so the domain would be all real numbers. What about the range? Well, let's see. For what values of y do we have points on the graph? Well, for this value of y, that value of y, this value of y, all the ones up here have spots on the graph. All the ones down here, turns out, have spots on the graph too. So the range would be all real numbers as well. Functions can be classified in a couple of different ways. One particular classification is called one-to-one. A one-to-one function, there are some fancy definitions of it, but basically it's graph. If you're talking about it graphically, it's a continually increasing or continually decreasing kind of function. We haven't talked too much about increasing and decreasing, but I think you know the idea. If it's decreasing, for example, from left to right on our coordinate plane, then it's kind of going down. If it's increasing from left to right, it's kind of going up. It might wave a little bit, but it'll never go down and then up. It's continually increasing. It might not increase as fast in some spots, but it's continually increasing. That's what one-to-one is all about. It kind of says that we already know, because it's a function, that for every x value there's only one y. But the one-to-one idea says that for every y value, there's only one x. You see, for every second component, there's only one first component, 1 to 1. Let's talk specifically about the graphs of functions. We've already seen the graphs of some functions just a bit ago, but I want to make sure that we can look at an equation and algebraically determine whether we have y as a function of x, and we can look at a graph and tell whether or not it's the graph of y as a function of x. You see, it's important that we be able to do those kinds of tasks. Here, a y equals x squared minus 2. The acid test when we're deciding whether y is a function of x is, does it meet the definition? That is, do we have a condition where for every x replacement we put into this thing, we're going to get exactly one y value? Every time we put an x in here, we're going to only get one y value, and that certainly is the case here. And here is its graph. Now, graphically, you can tell whether or not we have a function by saying, is it the case that for this x we have one y value? For this x we have one y value. For that x we have one y value. For these x's we have only one y value. That's the idea. It's, the failure comes when we have an x and it throws off two values of y, algebraically or graphically. Algebraically, the situation looks like this. So consider the equation x equals y squared minus 3. Suppose we choose a value of x like, oh, let's say 6. If x is 6, this becomes 6 equals y squared minus 3, adding 3 on both sides. And now by the square root property, y then is either plus or minus 3. And this means that for this value of x, for this one x value, we have two values of y. So 6 is associated with 3. 6 is also associated with negative 3, algebraically. Now this means then that y is not a function of x here. Graphically, it looks like this. Here's the graph of this situation. And from the graph, we can see even more plainly that for many values of x, we have two values of y. For this value of x, we have this value of y and this one. You see, we have an x with some value of y and the same x with the negative of that value of y, it turns out. So one value of x throws off two values of y, therefore this is not the graph of a function. It's for this reason, this idea that one x throws off two values of y, that we have a vertical line test for functions. We fail the vertical line test. That is, if we can draw a vertical line through the graph and it intersects the graph in more than one point, then it means that one value of x throws off two values of y, and therefore we do not have a situation where y is a function of x. Vertical line test. Now, in your book, there's a really nice illustration of some of the degenerate forms of familiar functions. There's the graph of f of x is x squared, x cubed, the square root of x, absolute value of x, 1 over x, sine x, cosine x. These are degenerate forms, or the simplest forms, for each of these kinds of equations or functions. And they often, from algebra, you might recognize that a lot of times when we had a discussion of a topic, and I think right away about the notion of rational functions. When you first studied that, you studied the nature of f of x is 1 over x, and you looked at its graph, and then you started to make changes and cause complications to occur here, and see how vertical and horizontal asymptotes occurred in this kind of environment. Well, all of these degenerate forms have transformations that are associated with them. And transformations are simply situations where we perform some algebraic operation, adding, subtracting, multiplying, dividing, whatever. And it causes, that change algebraically causes a familiar change in the graph, a predictable change in the graph. We can see it rather easily by looking at one of these forms. Let's take the parabolic curve. The parabola is the graph of the simplest quadratic. F of x is x squared. Now we know from our experience that if g of x is x squared minus 3, then all that does is throw the graph down 3 on the coordinate plane. This is the graph of x squared minus 3. Now, you know, when you learned about this, I'm hopeful that you learned in terms of concept. What's the general idea here? Well, it is that if this is the graph of x squared, then this is nothing but the graph of x squared down 3. You see, you know, we're talking about, for y values, we're talking vertical distances. That's a understood y value. So we're talking vertical distances. So it would be the same as those vertical distances, but subtract 3 for every one of them, you see. And if we take this vertical distance and subtract 3, and that vertical distance and subtract 3, and this vertical distance and subtract 3, and every vertical distance and subtract 3, the whole graph moves down 3 on the coordinate plane. And that's all there is to it. Another transformation is one that causes the graph to move left or right. This is a little more elusive to understand, but it occurs like this. If h of x is x minus 2 squared. Now, notice the difference between this h function and the g function over here. Notice here that the prevailing operation in our degenerate form is, let's say, squaring. So here we are subtracting 3 after that prevailing operation of squaring. So we're squaring and then subtracting 3. That causes the graph to move down 3 on the coordinate plane. Incidentally, if we were adding 5, it would move up 5 on the coordinate plane. So if we're adding 2, it would move up 2 on the coordinate plane. You get the idea. All right, over here, we are subtracting 2 before applying that prevailing operation of squaring. So we're subtracting 2 before the squaring takes place, and that's what causes the shift left or right. All right, so, and notice that the shift is in a direction that we don't expect. Now, the way you remember this is that if we have an operation that occurs before the prevailing operation, that is, if we add or subtract before the prevailing operation, then the graph will move left or right in a direction that we don't expect. Now, I say we don't expect it because minus 2, that's the minus direction. That's the negative direction left or right. Why do we move to the right 2? So it's a direction that we don't expect for that reason. And incidentally, a way to look at it, this isn't the way you'll remember it, but a way of looking at it is to say, well, we know what squaring all real numbers will do. Squaring all real numbers is just a parabolic curve whose vertex that opens up and whose vertex is at the origin. Okay, fine. That's the behavior of squaring all real numbers. But here, we're going to take all these real numbers and we're going to subtract 2 before we square. So that just means that I'm going to take this coordinate system. Let me look at it like this. Imagine fixing this rascal right here, and imagine taking this coordinate system, this x-axis, all right, and just move it south 2 places. Move it over 2 places. Just move everything involved in that over 2 places. Well, what would happen here is that this y-axis would move over 2 places, you see. All right, so we've moved the coordinate plane over 2, and the parabolic curve has behaved the same way that we would expect a parabolic curve to behave. It is the squaring of all real numbers, you see, and that's how it behaves. And so instead of the graph moving one way or another, really it's the idea that the coordinate plane shifted on us, you see, and but that's not the way we'll remember it. We'll remember it as if we add or subtract before the prevailing operation, we move left or right in a direction we don't expect. All right, that's another transformation. A third transformation is a reflection. This is negative x squared, and it's the parabola going opening downward. And you can think, again, it's the idea that y values are vertical distances, and these are just the negatives of those vertical distances that would cause the graph to open up. If the graph is opening up according to x squared, then minus x squared, or the negative of x squared, means all of those vertical distances are now going down, and so the graph goes this way. There's actually another transformation that we could discuss. It's a reflection. Now notice here we're reflecting in the x-axis. We could talk about a reflection in the y-axis, and that would occur here if we were talking about a function, let's call it h, g, h, k, let's say k of x is negative x squared. You see, notice now I'm applying a negative inside the parenthesis. Here it's sort of outside an understood parenthesis. This is the negative of x squared. And this is negative x squared. You see, so, but every time what we'll get is exactly what we had originally. It doesn't make any difference whether x is 2 or negative 2, the negative of either 2 or negative 2 when squared gives the same amount. All that means is, you know, we're doing a reflection, but we're reflecting in the y-axis, so the graph sort of imprints on itself. So we really don't have any discernible difference in the situation, but I do want you to know that there is another reflection that's possible. Let's talk about several transformations all at once. This is the way that a lot of times these elementary functions can be evaluated graphically. You can just imagine the graph just by noticing things and knowing things about the possibility of transformations. Here we have a parabolic curve. We know we have a squaring operation here, so we think about, okay, this is a parabola. Now where is it located? All right, let's decide. We start out with the idea, our imagination is starting with the parabolic curve right here. Something like that. And then we see, well, let's see, we see x plus 3. Adding 3 before the prevailing operation will shift that graph over to the left in a direction we don't expect 3 places. So this vertex will go 1, 2, 3 over, and now the graph ends up here. Okay. Now what about this minus sign? Well, the negative of this means that we are going to reflect in the x-axis. So now we think about the graph making an appearance here. And then minus 1 will take all of these vertical distances and move them down 1 on the coordinate plane. So the whole thing shifts down 1. This vertex goes to this point. And you know, I say the vertex, it's actually all points go down, but a lot of times a reference point is useful to notice. You choose a reference point, you move the reference point, all the other points are going to follow. You know, that's one way to look at it or to think about it very quickly. But anyway, the graph will end up in this position. You can verify this on the graphing calculator. Incidentally, the graphing calculator is very useful to experiment with these various transformations and to familiarize yourself with them and become comfortable with them. Let's talk about the square root idea. All right, f of x is the square root of x. Here's the basic function. I want to choose this one here because I want to show that other reflection that I was talking about. If g of x is the negative of x, of the square root of x, then we're talking about the negative of all of those guys. So these vertical distances, the vertical distances described here, are just the negatives of those vertical distances. So we have this reflection in our x-axis. So the reflection goes this way and the graph then looks like that. On the other hand, if we have the square root of negative x, then the reflection is in the y-axis, and so from here we're reflecting in that y-axis, so the graph shifts over this way and the graph looks like that. Now all of these transformations can be viewed symbolically. That is, we could look at the elementary transformations that we have here and compare them to the original. That is, this g function can be thought of as, now remember, f of x is x squared. So this really then is just f of x minus 3. Now notice the subtraction of 3 after the f of x. This, on the other hand, the h function, could be thought of as f of x minus 2. You see, this says in the f function replace x with x minus 2. And in the f function, here we are, replace x with x minus 2, and we have that. You see, and here this would be the negative of f of x. And let's slide over. Gee, we could even write this one in that kind of symbolic form. Let's try to do that. Now I have this listed as f of x. I want to rename it. I want to call it, let's call it k of x. And f of x we know to be the x squared. That's kind of our reference function here for this guy. And so let's just rewrite. Let's see, when we talk about the x plus 3 being squared, that is f of x plus 3. That's the x plus 3 squared. All right, then the negative out here, oh, that's negative, and then the minus 1. You see, so this k function is really just this, you see, symbolically. And over here, when we talked about the square root function, this negative of that is really just the negative of f of x. And that's that reflection then in the x-axis. And this one is, this is the one I really want to show you. This is f of negative x. You see, f of negative x. And that gives that reflection in the y-axis. In algebra, you talked about a lot of different kinds of functions, and I'd like to review some of those with you now. All of what we have talked about in terms of functions before can be classified as elementary functions. That's not very comforting. I know they weren't very elementary when you studied them, but mathematically they're classified as elementary functions. And basically there are two kinds, two groups of elementary functions. There are algebraic functions, and functions that are not algebraic are said to be transcendental. So we have talked about, we've never classified them this way or used this name probably, but they're called transcendental functions that are not algebraic. And algebraic functions are polynomial functions, radical functions, and rational functions. And we're going to talk a little more in just a minute about the polynomial functions, because by far this is the one or the type that we have dealt with more than any of the other types here. Polynomial functions would include linear functions and quadratic functions, you see, and a general family of functions that are of higher degree than the quadratic functions. So we spent a lot of time in this area. All right, we have a pretty good idea of what radical functions are all about. They have a radical in them. Rational functions are functions that are in the fraction form, where you actually have a polynomial in a denominator involved in the rational functions. Now the transcendental functions, the non-algebraic functions, are trigonometric functions, sine, cosine, tangent, and their inverses. Exponential and logarithmic functions, you recall that exponential and logarithmic functions as families of functions are inverses of one another. That is, every exponential function has a logarithmic function as its inverse, and vice versa. All right, let's talk a little about the polynomial functions, and I'm just going to blast through some terminology here just as a memory refresher. Don't expect you to understand all of this or to recall all of the details here, but I want you to know where you've been, because you've had a lot of exposure to this material. In polynomial functions, and here's an example of a polynomial function. We talked about these words of terminology. Terms, there are 4 terms in this polynomial function. Some of the terms are considered variable, and one is a constant. The variable terms involve letters, and the constant term does not. Coefficients, usually we're talking about numerical coefficient in almost all cases up to this point. When we refer to coefficients, we're talking about the number involved in a term. Here the coefficient is 2, here -5, here 3. Leading coefficient, we talk about degree, the degree of the polynomial, the degree of each term having to do with the exponent on a variable. And the leading coefficient is the coefficient in the term of highest degree. This term of highest degree also designates the degree of the polynomial itself. So there are just a lot of things that are related here in terms of terminology. Let's jump down here. What we did with polynomial functions is a lot of times we were trying to identify the zeros. And slide over here just for a moment. Let's look at it. You talked about zeros, you talked about solutions, you talked about x-intercepts, and these are pretty much interchangeable parts. In dealing with polynomial functions, you set the function expression equal to 0, and then you want the value or values of a variable that will cause that expression to become 0, and those values were called zeros. And those were also solutions. They're another term for those zeros is solutions, and graphically they're x-intercepts. So these are pretty much interchangeable ideas. Now in our quest for finding these zeros or solutions or x-intercepts, we perform certain tasks on the higher degree polynomial functions. There was a leading coefficient test. There was a rational zero test, Descartes' rule of signs, upper and lower bound rule. All of these blended together to help us analyze the situation with polynomial functions and determine the zeros. So we've done an awful lot with those. Also, we have performed operations on functions. Elementary operations would be operations like adding two functions together, subtracting them, multiplying them, dividing them. Very simple. But a more challenging kind of operation was the composition of functions. It was the idea of putting functions within one another, and I'd like to show you an example of that. If f of x is this and g of x is this, then f of g of x would be designated like this. Now here's the symbol or the notation for, this is sort of putting the g function into the f function. This is f of g, and sometimes we can actually put the x here, but it's intuitive as to what that means here. But it's f of g of x, and often it's better to write it like this. Even though these mean the same thing, it's easier to deal with if you see it like this, because our visual interpretation is a little easier. Let me show you what I mean. F of g of x. Well, g of x we know is this expression, so we could write f of, now let's see, g of x is the square root of x minus 1. You see, and now what does f of this mean? Well, it means in the f function, replace x with the square root of x minus 1. So in the f function, we're replacing this x with the expression square root of x minus 1. So we would have square root of x minus 1, then squared minus 3. And squaring the radical, we get x minus 1, and then collecting, we get x minus 4. So f of g of x are the composition of those two functions in sort of this direction gives us x minus 4. Now we can compose the functions in the other direction. We can put the f function into the g function, and the notation is like this. It's g of f, or g of f of x. And often, again, writing it like this makes it a little easier and more intuitive to flow through algebraically. F of x here we know to be the x squared minus 3 from above. G of this expression means in the g function replace x with this. So here's the g function. We're replacing x with the expression x squared minus 3. So instead of the square root of x minus 1, the x is replaced with x squared minus 3. That's the whole idea here in performing this task. It's just a little replacement. It's kind of a double replacement here to perform this entire task. Okay, so that's what the composition of functions is all about. Another designation or classification of functions is in terms of even and odd functions. And you may or may not have talked about this in the past, but we're going to refer to that notion from time to time in the future, so it's worthwhile for us to have some kind of definition or idea of what that means. It goes to the matter of symmetry, it turns out. Now, we talked about symmetry in an earlier section, and there were three types of symmetry, and two of those three were x-axis symmetry and symmetry about the origin. Remember, the x-axis the y-axis symmetry had to do with a reflection. If the graph reflects in the y-axis, then we have this y-axis symmetry. And for symmetry about the origin, it's sort of it can be thought of as either a double reflection, a reflection in both axes, or it can be thought of as a 180-degree twist about the origin. And either of those will accomplish that kind of symmetry. Now, symbolically, the y-axis symmetry can be described as f of x is equal to f of negative x. And in this circumstance, if this is true for the function, then the function is said to be even. Now, when we talked about y-axis symmetry earlier, we said, okay, here's how we test. for symmetry about the y-axis. Because we have this reflective quality, it turns out that anytime the point xy is on the graph, then negative xy is also on the graph if we have that reflective quality, you see. All of our horizontal distances can work in either direction. That's basically what it means. And so if we replace x with negative x, we should get an equivalent function. And we start with our equation or our function, and this is really f of x equals x squared minus 3, but I'll write it like this as the working model for our function. And we replace x with negative x, and we get what we started with. And so we say, yes, we have symmetry about the y-axis. But I want you to understand that in doing this, what are we writing? What is this? Well, this is f of negative x. You see, this is consistent with the symbolism or the notation that we have here. At any rate, this kind of function is said to be even. An odd function is a function that is symmetric about the origin, and the notation for that and the check for it can be illustrated like this. That given a function f, if the negative of f of x is equal to f of negative x, then we have this symmetry about the origin, and the function is said to be odd. Now, here's an example of the situation. I'm going to show the example in the way that we talked about symmetry about the origin before. And that kind of symmetry involved a double replacement. We said that if the point xy is on the graph, then the point negative x, negative y is also on the graph. And so that comes from that double folding idea. But at any rate, if this is our equation, then we replace y with negative y and x with negative x and see if we can manipulate this to the original position. And it turns out that the cube root of negative x is the same as the negative of the cube root of x, and multiplying by or dividing by negative 1 on both sides gives us the equation that we started with. Okay, so that is the way that we would have verified symmetry about the origin for this equation in the past. Now we can use this notation to perform the same task. That is, if we have this, then, you know, in the function notation we would have f of x is the cube root of x. Okay, so we would have this. Now, what does it mean to write the negative of f of x? Well, the negative of f of x would be the negative of this. And what is f of negative x? Well, it means in the f function replace x with negative x. So we would have this. Now, are these two equal? Go like this. Yes, they are the same. They are equivalent to one another, and therefore we have this kind of symmetry. Incidentally, to see that these two are indeed equivalent, let x be replaced with, let's say, 8. So this would be the cube root of 8, the negative of the cube root of 8. The cube root of 8 is 2, so this would be negative 2. If x is 8, then this would be negative 8. The cube root of negative 8, negative 2, negative 2, negative 2. So these are indeed equal to one another.